meta issues. One is sort of just tell you a little bit about how we've organized the lab and how we've been able to build, you know, a real impactful system, really built largely, almost exclusively by graduate students, that's had real impact in the industry. Because there's been some, a lot of changes in the way the industry is working that's made that a lot easier than it used to be. And then also, I want to talk a little bit about big data and data science and what all that stuff means, because there's a lot of excitement around it. There's also a lot of skepticism in terms of, you know, what's really there, what are the research issues, and so on. So kind of a big agenda. We'll see how much of it I get through, but why don't we just jump in? So this is just kind of a snapshot of a bunch of news articles written over the past couple of years about some of the software that we've been building in the App Lab. You might have heard of a system called Spark. That's what I'll be talking a lot about today. It's now called Apache Spark because we donated it to the Apache Foundation. But there's a whole set of analytic software that we built that as we've been releasing it, it's been adopted in various ways by people in the industry. And so this is just some of the press we've gotten on that. This is an article I actually found on the flight over here, where this is a Google Trends graph, right? So it's just a scaled. That's why there's no lines on the y-axis, but it's just a scaled representation of the frequency of searches for different terms. And the red is Apache Hadoop, which hopefully, since you're here for a big data talk, you've at least heard of, right? That's sort of the default computational engine that people are using for big data. That's the red, and that started, you know, around 2008 and went up from there. The blue is our system, Apache Spark, which we released in 2010, but nobody noticed. But, you know, very recently people started noticing, and what this article was about is that, you know, finally, you know, last month or something, those lines crossed. So there's actually more people on Google searching for Apache Spark than are searching for Apache Hadoop. So, but, you know, whether that means anything or not, it just gives you some feel for what we've been able to do. Okay, so I think I actually told you what I want to do. I want to talk about big data, what that means a little bit, to talk about the software we've built, and then I want to kind of jump up a level and tell you about how we organize our research, because there's some interesting things in there, and then, you know, kind of just wrap up with some thoughts on what's next and where things are going. So go through this quickly, but, you know, why are people so excited about big data? There's a lot of reasons. Some of them are more justified than others, but the thing that's true for sure is that just about everything we do is becoming data-driven. And so this is just a, you know, sampling of areas that are just generating huge amounts of data. So, you know, the one that's probably the most obvious to computer scientists is this one here, where it's just as more and more activities move online, there's just more and more data being generated about those activities. And what you might not, I think probably most of you realize it now, but when you do something as simple as like clicking on a link on a web page, or even worse, clicking on an advertisement, that sets off this whole cascade, right? The site you're visiting will record the fact that you did that. But more than that, you know, sites that you don't even know exist are recording the fact that you did that. And recording a bunch of things underneath in terms of the systems that are serving up that data, you know, the underlying backend systems that are maybe generating transactions that resulted from you clicking on that link and so on. And so one little activity online just generates this flood of information, okay? And so, and that's not going away, you know, it's just increasing, right? So mobile devices and so on. Another place where a lot of data is coming from, although not nearly the same amount of volume, is user-generated content, but it's valuable in its own way. So, you know, people tweeting, posting things in social networks and so on. Internet of Things or machine-to-machine communication is obviously another area where increasing amounts of data are being generated. And then finally, this one I'll just mention, especially those of us at universities, this is really important, is that basically all areas of science are becoming data-driven. So this is a graph that might be a little hard for you to see, but it's over time, it's on a log scale. This kind of boring straight line, that's Moore's law, right? That's the thing that us computer scientists are, so proud of, right? That every 18 months, that means you get twice as fast or twice as cheap or twice as dense, whatever you want to measure. This line here is the cost of sequencing genomes, okay? And the one thing you'll notice is that is dropping, much faster than Moore's law. So if you're doing genomics work, basically your computers are getting slower and slower every year relative to the amount of data that you have to deal with. Okay, and this is happening across, any field you can think about, whether it's, astronomy or, physics or, social sciences or whatever. Everyone's seeing this huge explosion in data. So, one reason people are so excited about big data is it's just everywhere, okay? And there aren't really any signs right now that it's going to slow down. Okay, so let's try to piece apart a little bit about what this term big data means, right? Because it's a little bit of an unfortunate term. People get hung up on the word big, okay? And so this is one definition that I really don't like, which says, well, it's, data sets that contain billions or trillions of records, okay? And, that's an obvious translation of big, right? But it's not a very useful one, right? So, there's a couple of things that are wrong with this definition, right? One of the most obvious ones is, well, if you have 1 billion minus 1 records in your database, does that mean it's not big data? Right? It's kind of crazy. And furthermore, in 10 years, this is going to look silly, right? Oh, you only have 1 trillion records? That's nothing, right? So, it's just not a scalable definition in either direction. Okay, so there's got to be more to it than that. So, the other thing I don't like about this is that it defines big data as a problem. Okay, I've got all this data and somehow I have to do something. Right? This is terrible. Okay, well, I'm a database person. I love having data, right? So I'd like a definition that doesn't define data as being a problem. So here's a kind of something that's heading towards a better definition that I found was useful. So it was from a pamphlet from the O'Reilly group, which is one of the groups that's really been out in front of the data science and big data movement. And basically what this quote says is it's about a breast cancer treatment. And it says that for a long time we thought this treatment was roughly 80% effective for patients. But now we know a lot more than that. We know that it's 100% effective in about 80% of the patients and completely worthless in the rest. And the trick is, right, that's kind of a funny definition. It's kind of a funny statement, right? Because in some sense it looks like maybe it's saying the same thing. But it's not, because the difference between the top statement and the bottom statement is that if you can collect enough fine-grained data, you can actually figure out who's in that 80%. Okay? So you can so it's not a random, it's not a roll of the dice whether this thing's going to work or not. You figure out who are the people that this drug works for, and you give them the drug. And for the other people that it's not going to work for, you try to, you find some other solution. And so, where this comes from is from the way sort of clinical trials have traditionally been done, right? If you were doing 80% is a good number. But if you were doing a clinical trial and your results showed you that the drug you're testing is, effective in 1% of the cases, you throw it away. You say this thing's completely worthless. But if you could figure out exactly who that 1% is, you can save a lot of lives that way, right? So it's all about being able to collect enough detailed information. And so the idea of big data, to my mind, is that there's a certain tipping point, right? That you're collecting data, either more data about more individuals, or finer grained data, right? So over smaller and smaller time intervals, or maybe wider data, right? So you're collecting more features and more dimensions. But at some point, you get to see things that you wouldn't get to see if you didn't have all that data. Okay? And so that to me is what big data is about. That there are certain phenomena, certain things you can discover only when you've collected enough information at the right time. And that's basically saying that big data is an opportunity. So if we can figure out how to make sense of these increasing amounts of information we're getting, we can solve problems that we wouldn't be able to solve if we didn't have that data. That, to me, as a researcher, is a much more interesting situation. Okay, so big data is an opportunity. So, here's another way of thinking about it. This is an application we built in our lab. It's called Carrot. And what Carrot does is it runs on your smartphone, and it watches what applications you're running and what's happening to the battery on your device. And periodically, it uploads that information to an application that we're running in the cloud. Okay. Now, when you run Carrot with 50 phones, which is the way we tested it, you basically learn nothing. There's nothing interesting. Okay. But Carrot's been downloaded. This is an old slide. It's been downloaded about 1 million times. Okay. Now, when you can collect data from 1 million different phones, you can start to build models about, for a particular phone, running a particular version of an operating system, which applications are correlated with heavy battery usage and which ones aren't. So that way, you can collect that information, you can then report back to each individual phone, hey, here are things that you're running on your phone that everybody who has your phone, it drains their battery, okay? So we can make predictions. In fact, if you stopped running this application Pandora, we'd expect your battery would last an extra hour and 27 minutes. And we know that because we looked at all the people who have your phone that weren't running Pandora, okay? So that's, again, if you didn't have enough data, you wouldn't be able to figure that out. The other thing we can do is we can say, hey, whenever you run Google Maps, your battery drains really quickly, but most people with your phone that don't have that problem. So maybe you need to reinstall Google Maps, right? So you can do both. You can find the patterns and you can find the outliers, okay? And so, this is kind of, maybe you might think of kind of a simple problem of how long is the battery going to last on your phone? But imagine if this was a medical application where you're trying to come up with a precision prescription for an individual with a particular problem, right? So that's, again, sort of the power of having a lot of data. Okay. So we talked about this. So we're, a bunch of us at Berkeley got excited about big data. Actually, before it was, well, it doesn't matter, but it wasn't really called big data. We started looking at, it was probably about 2009 that we started working on this. But we got a big boost when we got this award for, so the White House, the U.S. president decided that big data was going to be important, started this big initiative, and we were lucky to be able to be part of the projects they announced when they funded that first part of the initiative. So what are we doing? It was actually in that quote, but what our approach is we basically said there are three classes of resources that you have available to make sense of big data. Algorithms, right? So think about machine learning, statistical processing, and so on. Machines, cloud computing, scalable clusters, warehouse scale computing, and so on. And then the P is people. So you can think about people that are interacting with the data, like analysts and data scientists, or kind of, from my point of view, kind of more interestingly, you think about using the crowd to find data for you, to clean the data, to help answer the questions that the algorithms and the machines can't quite do yet. Okay? And the idea of our project is to say, all right, we have these three very different types of resources. How do we put them together into a single system, to solve a given data-driven problem, okay, or to answer a certain question? So that was kind of what we set out to do. Okay, so now I want to focus more on this analytics stack that we've built. And to understand what we've done, it's interesting to kind of look back a few years. So a lot of the excitement in what people are calling now, the big data ecosystem, started because a number of big web companies realized that they were going to be faced with these huge amounts of data. And they felt that either the existing solutions, like existing database systems, couldn't scale to handle those data volumes, or even if they could scale that big, they were going to be too expensive. So they started implementing their own systems to process large amounts of data. And so, this is companies like Google, Yahoo, Amazon, and so on. And the thing that really caught people's attention was a system called MapReduce, which was developed at Google, and basically lets you write at a pretty low level programs that are highly parallel. So as you get more and more data, you can add more and more machines, and you can still process, you can still keep up with the data volume. What really caused this to take off is that people that were at Google and places like that were used to this type of technology left, right? They went on to other companies, and they realized that they needed those types of tools. In particular, there was a group that built Hadoop, which we've already mentioned, which is basically an open source version of MapReduce. So MapReduce, initially you had to be at one of these companies to get access to this technology, but once it was put into the open source, everybody could get it. So a lot of people got excited about MapReduce, and they said, hey, this is great. I can now run scalable computing, right, which is something they couldn't do before. Especially they couldn't do it, with free software. And they said, it's great, except that, I've got a special problem, right? I don't have, I'm not doing this generic, computing PageRank or whatever that, that Google was doing. I'm working with stream data, or I'm running SQL queries, or I'm working with graph data. And for each of these problems, somebody said, okay, I'm going to take this MapReduce idea, this ability to spread computation across all these different machines. I'm going to specialize it. So I'm going to build a version of the system that runs SQL. Okay, it doesn't do anything else, it runs SQL. Or I'm going to build a version of the system that lets me run graph algorithms over it. Okay, it can't do anything else but it'll do graph algorithms, and so on. Okay, so there was this explosion of different systems that all solved some specific problem. But, the problem here is if you wanted to solve kind of an end-to-end data problem, you'd often have to use a bunch of these things. And they weren't built to work together, okay? And so what you end up doing is having to learn a bunch of different systems, having to keep track, right? These things are all open source. They're changing constantly. You have to keep track of all these different systems. And then when you want to move from one set of processing to another, typically what you had to do was take the data, copy it out of the system that you had it running in, and load it into another system. Okay, and then copy it out and load it into another system, which for big data is basically the worst thing you can do, right? Because you don't want to have to move that stuff, and you certainly don't want to have to convert it. Okay, so this is kind of the state of the art in the big data ecosystem. So what we did is we came at it from a different way. We said, all right, we like MapReduce too, but why don't we try to do something else? And instead of specializing MapReduce for every problem, let's try to generalize it. Let's try to make it bigger, okay? And it turns out that there are two additions that you need to make to Hadoop to make it much more general. One is you have to have more than map and reduce, right? So MapReduce is called that because there are two things you can do to data. Map is apply some function to individual records. Reduce is take a collection of records and smash them together. Okay, that's map and reduce. You want to do more than that. Okay, and so you want other operations, okay, and you want other patterns. And the second thing is between each of those operations, you want to be able to share the data. So you don't want to have to, write the data out to disk and then read it back in. Okay, and what we found was just with these two extensions, you can implement SQL, you can implement streaming, you can implement graphs, you can implement machine learning libraries, okay? And obviously, there's a lot of benefits to this, right? If you're a user, you don't have to learn a bunch of different disparate systems, you don't have to track them all, you don't have to, worry about which pieces to put together. And, if you're doing an operation that requires a few of these different things, you don't have to move the data from system to system. Right? So we built a system called Spark, which is basically our substrate, on top of which we built the rest of the stack, which is all these other types of functions. Right? So what I want to talk to you about is kind of the overall structure, and I'll spend more time on Spark just so you see what we did there. Okay, but that was the basic idea. Instead of building an individual implementation of something that looks like MapReduce to handle every access pattern I could think of, let's try to generalize that lowest level and be able to build all our different interfaces on top of it. We can have a unified system. Okay, so that's what we did. We built this thing called the Berkeley Data Analytics Stack. The acronym is BDAS, and we pronounce it badass. And and this is what it looks like. And you kind of have to read this from the bottom up. So at the lowest level, we do resource virtualization. And there's two systems there. One we built, one we didn't. So the legend here is the blue things are things that we built in the lab, and the gray are things that were built elsewhere, but that we work well with. So at the lowest level, you want to be able to take a huge room of machines and split it into individual clusters virtually, so that you can share it among different users and have different, instances of the system running and so on. So we built a system called Mesos in the lab, and eventually that got released as an Apache project. There was another project that came along later called Yarn that got quite popular, so we play with Yarn as well. Okay, but that's at the lowest level, is take physical machines and virtualize them. The storage layer, we use existing systems again, so we're big fans of the Hadoop file system, which is a wonderful scalable file system. You basically just add more disks and throw more data at it. It just grows and grows and grows. And so there are people with HDFS implementations with many petabytes of data sitting on them, which is a scale that you really just didn't see before. Yeah, most people didn't see before. And we built on top of that an in-memory caching layer called Tachyon. Okay, and underneath Tachyon, we can have different file systems. So Amazon file system. I don't have the whole list here. There's a system called Bluster. Ceph is another one that's used in scientific applications. There's a whole bunch of file systems that sit under Tachyon. And then the fun really starts up here. So our main processing engine, which we're going to talk about, is Spark. And as I mentioned, that's now an Apache project. That I was showing you the popularity of it. I'm not going to talk about this today, but ask me questions. I can try to answer. But Spark was meant to solve analytics problems, so kind of batch analytics mostly. Velox is meant for serving. So Spark applications tend to work. You get data, and then more data comes in, and you process it, but you don't really touch the old data. Velox is meant for data that's constantly being updated, so it's a little more transactional. Okay, and this is a new part of the system we're building. And then, the real action is up here. So we have a bunch of different ways of getting at the data. There's a streaming engine. There's a query processor. There's a graph system I'll tell you about. There's a library of machine learning functions. There's an approximate query processor. There's a human crowdsourced data cleaning module. There's a declarative machine learning system, so you don't have to say exactly how to implement your machine learning, but just at a high level what you want to do. And then there's even an implementation of the R statistical language that runs on top of Spark. And then on top of that, we have a bunch of applications that we built, and I'll tell you about some. I actually already told you about the one for cell phone battery debugging, but we're doing stuff in Internet of Things, and we've done some stuff in genomics. I'll tell you a little bit about that. But this is what we've managed to build in the lab, and some parts of it are more baked than others. But Mesos is out of the lab, and there's companies around it, and lots of people using it. Spark is largely out of the lab now. And again, there's companies. I'll show you some of the traction that we've had there. And then a bunch of these other components are in various stages of alpha and beta release. Some of them have been baked into Spark. Okay, but that's kind of the view of our system. So what I want to do is talk a little bit about Spark, because that's kind of the heart of the system. Oh, nice. All right. So I showed you that curve at the beginning of the interest that sort of happened in Spark over the last year. There's a bunch of reasons for that. Not all of them are technical. But I love this quote here that just says it's only September. I found this in September, but it's pretty clear that 2014 is going to be the year of Apache Spark. And Apache Spark goes back to this paper that we wrote for a workshop back in 2010, where we laid out the architecture of Spark. But so basically from 2010 as a workshop paper to 2014 is basically being a big deal in industry. It's about as fast as things go in terms of technology transfer. And I want to talk a little bit about how that happened, a little later. Okay, but what is it? Spark came from a very interesting place. We had a lab that was basically a combination of computer systems people and machine learning. And the machine learning people were trying to run some algorithms on Hadoop, and we're just getting terrible performance. And started talking to some of the students who worked on the systems and said, hey, can you help us debug this? What are we doing wrong? System students looked into it and said, no, you know what, you're not doing anything wrong. The problem is that the application you're trying to run, this algorithm you're trying to run, isn't the kind of thing that Hadoop was meant for. And in particular, what they were trying to run was an iterative algorithm that basically goes over the data, multiple times before it computes. And so the way this looks in MapReduce is you start off with an initial model, you read in your training data, and then you apply a function to each individual record, and then you can combine the results, and then you basically learn a new model. Okay, and so you come out with a new model. Then you go through and you iterate. You take the new model, you apply it to the training data, right? Map, reduce, you come up with a new model again. And you keep going. Okay. Now, why was this a problem for Hadoop? I'll show you. Okay. So let me go back. So the problem is that the way Hadoop is working was that it basically, for each iteration, it would read things in from disk, it would process it, it would write things out from disk. And then when you iterate again, it would start as if it was a completely new program. It would read the training data in from disk again, it would write stuff out to disk again, and you keep doing that. And so you're basically, each iteration is communicating to the disk, which is about the slowest part of the system. So, one is that every iteration loads the data. So that's that. Then you're redundantly saving the output, right, in between every stage. Okay? And so if you think about it, this is what you're trying to do, right? You apply map, you reduce, you do that to the disk, you read more data in, you write that out to disk, and so on. And so if you think about this for not very long, you realize that, well, what you want to do is basically read stuff into memory once. Okay, so you don't have to repeatedly read it from the disk. And the second thing you'd like to do is stop communicating through the disk drive, right? So you'd like to do that sharing between different stages of the program. Okay, and so this is basically what Spark does: is it takes the map reduce paradigm, and it's smart, and it's basically smart about when you cache things in memory, and that you can tell different stages of the program to look at memory for data rather than having to read it from the file system. Okay, so it sounds like a simple idea, and it really was. Probably why it took off. Okay, and what you end up with is, well, here's the result. So, if you run Hadoop, basically this is how long it takes to do one iteration, that's the blue. If you want to do 10 iterations, it's about basically 10 times that. If you want to do 20 iterations, it's about 20 times the cost of a single iteration, and so on. Whereas with Spark, you pay a price to read things in at first, okay, but then the incremental cost for every subsequent iteration doesn't have the I/O cost, and so you're just doing the computation. And in this case, computation was really, really simple. Okay, and in a lot of machine learning algorithms, computation is really simple. You're just doing it over a lot of data. And so on applications like this, you can get speed ups of 10 or 100 times over the Hadoop MapReduce, which is what people were using. Okay. There's also advantages if you're trying to run queries on the system. You read the data in once, and then all the queries can access the data in memory. Seems if you're a database person, it's like, well, how else would you do it? But if you look at the SQL processes that run on top of Hadoop, they read the data in for every query. It doesn't make sense. So that's kind of the big idea in Spark. And then you might be thinking, well, geez, that was easy. So what's kind of the intellectual contribution? Why did Batei Zaharia, the guy who did this work, why did he get a PhD for this? It's a reasonable question. And the reason is because what Batei figured out was really actually quite beautiful. And he came up with with an abstraction that underlies Spark called Resilient Distributed Data Sets, or RDD. And RDDs have a couple interesting properties. One is that they're immutable. Okay, so when you create an RDD, you can't change it. Okay. The second thing is that there's a set of, all you can do to an RDD is basically transform it into a new RDD. So there's basically a library of transformations that say, given some input RDD, apply the transformation, get an output RDD. Okay? And so that's the abstraction. And then, underneath that abstraction is all the mechanism to figure out when the RDD is too big to fit on a single machine. How do you spread it across all the machines in the cluster? And how do you keep track of the different processing that's going on the different machines? Okay? So the amazing thing, though, is this simple model, right? Sets of data that are distributed across a cluster that you can't change. And then a fixed set of coarse-grained transformations that take you from one of these collections to another collection. Right? That simple interface, right, that very narrow interface, was sufficient to implement all those models that I showed you in the previous slide. So you could do graphs, you could do SQL, you could do streaming, right? You could do machine learning. Right? That's what was beautiful about it. It came up with sort of the simplest set of abstractions, the narrowest interface you could come up with, and still implement all those things efficiently. Right? And so that's what sits at the heart of the Spark system. Now, when I talk about generalizing MapReduce, this is what I mean. These are a subset of the operators that you can run on an RDD. So the first thing you can do to an RDD is you can run map.